Check your smartphone battery. It contains roughly 0.01 ounces of cobalt. Your laptop holds 10 times more. Electric vehicles require 30 pounds per battery pack. This bluish-gray metal, rarer than platinum, enables rechargeable batteries powering modern civilization. Global demand exceeds 200,000 tons annually, growing 20% yearly. One nation controls 70% of supply. Democratic Republic of Congo, where cobalt mining represents technological progress built on human suffering. How does obscure metal buried in African soil become indispensable to iPhones and Teslas? Why can't battery manufacturers escape dependency on ethically compromised supply chains? Stay with us. You'll witness industrial-scale extraction reshaping Congo's landscape and discover cobalt's devastating secret. The green energy revolution runs on metal mined by children. Kolwezi district in Congo's Katanga province contains world's richest cobalt deposits. Ore bodies stretching 40 miles containing 8 million tons of recoverable cobalt. Glencore's Mutanda mine dominates the landscape. Open pit 2 miles across, descending 1,000 feet. Giant haul trucks, each carrying 400 tons, create spiral roads visible from space. This single operation produces 25,000 tons of cobalt annually, enough for 5 million electric vehicle batteries. But industrial mining tells only half the story. Surrounding the massive pit, tens of thousands of artisanal miners, cruciers, dig by hand. They tunnel through unstable soil with shovels and pickaxes, extracting ore from shallow pits and abandoned mine shafts. No safety equipment, no ventilation. Children as young as 7 work alongside adults, earning $2 daily. The contrast is staggering. Billion-dollar machinery operates next to subsistence miners dying for scraps. This is Cobalt's duality, cutting-edge technology enabled by Stone Age extraction. The ore, heterogenite and kerolite, contains 3 to 8% cobalt, always mixed with copper. Massive crushers reduce ore to gravel. Ball mills grind further, creating powder fine as flour. The grinding buildings operate continuously, deafening roar as steel balls pulverize rock. Each ton processed yields 60 pounds of cobalt and 300 pounds of copper. Cobalt is byproduct, making economics complicated. Flotation separation begins in enormous tanks containing chemical froth. Copper sulfides attach to bubbles, floating to surface for collection. Cobalt remains in solution, requiring different chemistry. The process generates massive waste. For every ton of cobalt extracted, 200 tons of tailings remain. These waste ponds, acidic and toxic, stretch for miles. The environmental damage is permanent. Soil contaminated for centuries, groundwater poisoned indefinitely. But demand doesn't care about consequences. Battery manufacturers need cobalt, whatever the cost. Cobalt concentrate undergoes hydrometallurgical processing. Chemical extraction replacing traditional smelting. The concentrate dissolves in sulfuric acid at 180 degrees. Copper precipitates first through pH adjustment, then cobalt gets separated from nickel and manganese through solvent extraction, organic chemicals selectively binding cobalt ions. The chemistry is precise, requiring exact pH, temperature, and reagent concentrations. The result is cobalt sulfate solution, pink liquid containing 20% cobalt. This solution ships to refineries, mostly in China, where final purification occurs. Electrolysis deposits pure cobalt metal onto cathodes, sheets of cobalt growing atom by atom from solution. The metal emerges silver pink, hard and brittle. But most cobalt never becomes metal. It stays as cobalt sulfate or cobalt oxide powder, the forms battery manufacturers require. The entire supply chain funnels through Chinese refineries, controlling 80% of global processing capacity. Battery-grade cobalt demands extreme purity, 99.8% minimum. Impurities like iron, nickel, calcium cause battery degradation. Quality control happens through mass spectrometry, analyzing samples to parts per billion accuracy. Rejected batches get reprocessed. Nothing wastes when material costs $60,000 per ton. The powder gets carefully packaged in sealed drums, each containing 500 pounds. These drums travel to battery manufacturers, LG Chem, CATL, Panasonic, the companies powering Tesla, Apple, Samsung. The cobalt combines with lithium and nickel in precisely calibrated ratios. Lithium provides energy density. Nickel adds capacity. Cobalt delivers stability, preventing thermal runaway, the catastrophic failure causing batteries to explode. Manufacturers desperately seek cobalt-free alternatives. None work as well. The chemistry is frustratingly specific. Inside battery factories, cobalt powder mixes with lithium and nickel oxides, creating cathode material. This mixture gets coated onto aluminum foil in layers thinner than human hair. The precision is absolute. Coating must be uniform within 2% variation. Any inconsistency creates hotspots during charging, potentially causing fire. The coated foil, along with graphite-coated copper anode and separator membrane, gets wound into cylindrical cells or stacked as prismatic cells. These cells fill with electrolyte, lithium salt dissolved in organic solvents. The electrolyte allows lithium-ion movement between cathode and anode during charging and discharging. Each cell undergoes formation cycles, controlled charging that activates materials and identifies defects. Failed cells get disassembled, materials recycled. The waste is too valuable to discard. Battery recycling could solve cobalt shortage, but currently only 5% gets recycled. The process is challenging. Batteries contain diverse chemistries mixed with plastics and electronics. Shredding risks fires from residual charge, but economic incentive grows. Recycled cobalt costs 40% less than mined material. Hydrometallurgical recycling dissolves batteries in acid, separating metals through selective precipitation. The recovered cobalt, lithium, and nickel return to battery production with identical performance to virgin materials. The circular economy remains theoretical. Most batteries end up in landfills or incinerated, cobalt lost forever. Companies like Redwood Materials and Li-Cycle are building recycling infrastructure, but scale remains insufficient. By 2030, experts predict recycled cobalt could supply 30% of demand. Until then, Congo's mines run continuously, extraction accelerating despite consequences. Cobalt derives its name from German Kobold, goblin, because medieval miners blamed goblins when cobalt ore poisoned them during silver extraction. For centuries, cobalt's only value was blue pigment in pottery and glass. Everything changed when John Goodenough invented lithium-ion battery in 1980. His cobalt oxide cathode enabled rechargeable batteries light enough for portable electronics. Sony commercialized the technology in 1991, launching the mobile revolution. Initially, cobalt demand remained modest. Cameras, laptops, phones used small batteries. Then electric vehicles emerged. A single Tesla Model S contains 24 pounds of cobalt, equivalent to 1,000 smartphones. As EV adoption accelerates, cobalt consumption grows exponentially. By 2030, transportation will consume 60% of global cobalt supply. The metal that poisoned medieval miners now powers humanity's energy transition. Irony lost on nobody. Carbon emissions perspective shows paradox. Electric vehicles reduce emissions 80% versus gasoline cars over life cycle. But mining cobalt generates massive environmental damage plus humanitarian crisis. Children in Congo work illegal mines, exposed to dust causing respiratory disease, digging tunnels that collapse regularly, earning subsistence wages while battery companies generate billions. Amnesty International documented children as young as 6 mining cobalt sold to major tech companies. The supply chain is deliberately opaque, or changes hands multiple times before reaching refineries, obscuring origins. Here's the secret we promised. The green energy revolution cannot exist without ethically compromised cobalt. Every Tesla, every iPhone, and every laptop depends on metal extracted under conditions violating international labor laws. Battery manufacturers know this. They issue statements promising ethical sourcing while buying through intermediaries, providing plausible deniability. The truth is uncomfortable. Transitioning away from fossil fuels requires accepting different moral compromises. We've replaced oil fields with cobalt mines, exchanging one exploitation for another. From Congo's pits to Silicon Valley's gadgets, the transformation completes. We've created technology liberating us from combustion engines while enslaving miners and supply chains we refuse to acknowledge. That electric vehicle representing environmental consciousness contains metal mined by children. The battery in your pocket enabling instant global communication required someone else's suffering to exist. Progress always demands sacrifice. We've just decided others should make it. Cobalt doesn't just power devices, it exposes civilization's willingness to ignore atrocity for convenience. We know the cost. We pay it anyway. Every year, billions of people around the world press the same pedal, and they don't even realize it was slowly killing them for decades. What was supposed to save lives quietly filled the air with poison. Why did a material once considered perfect vanish almost overnight? And what replaced it? There's one detail brake pad ads never mention, but it's what determines whether your car stops in that critical split second. Today, these pads withstand hell itself, don't smoke, and leave barely a trace. But the road here was deadly dangerous. Stick around till the end, and you'll discover which hidden component once cost millions of lives and why modern factories guard their formulas like state secrets. In the 1920s, every brake pad contained asbestos, fibers that could handle 1500 degrees Fahrenheit and wouldn't wear out. But every tap of the pedal released microns of poison into the air, settling in the lungs of drivers and pedestrians. By the 1990s, asbestos had killed millions. Lung cancer, mesothelioma. Europe banned it first in 1998. Manufacturers scrambled to find a replacement. Organic compounds made from rubber, glass, and metal fibers. The first non-asbestos pads braked worse, overheated at 750 degrees, and released the rotor. But it was a start. Today, the top choice is ceramic composites. The base is ceramic made from silicon nitride and silicon carbide, mixed with copper fibers for heat dissipation. The material withstands 650 degrees without deforming, doesn't squeal, and doesn't dust. Ceramic makes up 40 or 50% of the mass, reinforced with steel fibers for strength. At 500 degrees, regular pads smoke. Ceramic ones stay cool as ice. In this massive plant, something is born that'll save your life on the road. Manufacturing ceramic brake pads isn't just mixing powder with binder. It's precise science involving pressure, fire, and high-precision machinery. Each pad weighing 7 ounces has to survive 600 degrees of hell, not crumble, and not let go of the rotor. Let's break down the process step by step, from raw materials to finished kit. Everything starts with hoppers full of powders. The main ingredient, ceramic, meaning silicon nitride silicon carbide, a white powder hard as diamond. They add copper fiber for heat dissipation, thin threads the width of a hair, graphite for smooth grip, reinforced glass for strength, barium sulfate for stability at high temperatures. Each recipe is a factory secret, like the Coca-Cola formula. In giant mixers with a 500-gallon capacity, powders are combined in precise proportions. They add liquid wax-based lubricant, 5 or 7% by weight. The mixer spins for 30 minutes at 50 revolutions per minute, transforming dry powder into a uniform wet mass, like bread dough. Temperature is held at 100 degrees so the lubricant doesn't freeze. The result is raw dough weighing 1,100 pounds, ready for forming. The mass goes into a rotary press, a machine with 20 tons of force. They pour 550 grains of the mixture into a metal mold measuring 6 by 2.5 by half an inch. The top plate descends with 285,000 pounds per square foot of pressure, like parking a tank on your palm. In 10 seconds, the dough compresses into a monolithic green blank, 3/4 of an inch thick. The pressure squeezes out all the air, creating a density of 175 pounds per cubic foot. The press runs in cycles, 60 blanks per hour. Each comes out perfectly smooth with a friction surface angled at 5 degrees for better disc contact. The blank's still brittle as cheese, but it already has the shape of the future pad. The most critical stage? Sintering. Green blanks go onto steel trays, 50 pieces each, then get pushed into a tunnel kiln 100 feet long. Temperature rises gradually. At peak heating, 4 hours in, the ceramic melts. Copper fibers fuse. Graphite crystallizes. Total sintering time, 12 hours. Finished pads, gray-silver monoliths. Go to inspection. A laser scanner checks dimensions accurate to 1/100th of a millimeter. Ultrasound checks density and cracks. 2% get rejected. Next, grinding. The machine removes 1/2 millimeter from the friction surface for perfect geometry. Edges get rounded to prevent squealing. They apply a protective coating, a thin layer of molybdenum disulfide for that first soft breaking. Laser marked, then assembled into kits, 4 pads plus springs plus backing plate. The final test, the simulation stand. The pad is pressed against a disc spinning 2,000 revolutions per minute for 200 cycles. Acceleration, then hard braking up to 6,000 degrees. They check wear, squealing, dust. Ceramic pads pass without smoke. Metal ones squeal. A finished pad wears out after 30,000 miles. That's normal wear. With aggressive driving, it wears out after 18,000 miles. The U.S. market operates with 131 facilities, which has decreased by 0.6% in recent years due to automation. Production is tied to the automotive industry. Rising car sales drive demand, especially for pad replacements in trucks and passenger vehicles. Key trends: shifting to eco-friendly materials without copper. California capped it at 0.5% starting in 2025, which cut pollution by 28% statewide. Imports matter, but tariffs affect local production. The leaders are the southern U.S., specifically Texas, Alabama, Tennessee, with Ford and GM plants. The European brake pad market shows steady growth at an average annual rate of 4.7% through 2028. In Germany, the market leader volume will hit nearly $320 million by 2028. France is growing at 5.5% annually, the UK at 3.8%. Metallic pads are still popular and hold 25% of the EU market because they're cheap for trucks and Porsches. But their dust is a problem. Steel and copper settle on roads, get into water and lungs. Ceramic cuts emissions by 80% compared to these semi-metallics. And besides asbestos and metallic pads, there was an attempt to make organic ones. These are pads from the 2000s, the first mass replacement for asbestos. The base is synthetic rubber, fiberglass for reinforcement, Kevlar or aramid fibers for strength, plus barium sulfate and graphite. The soft compound gave a quiet bite. Little dust, didn't scratch rotors. But at 550 degrees, they lose 30% of their stopping power, which works for daily driving but not for sport.
Hold a car battery. It weighs 40 pounds. 30 of that is pure lead. Every year, humanity produces 11 million tons of this heavy, soft metal. Romans used it for plumbing 2,000 years ago. We banned it from paint and gasoline because it poisons children's brains. Yet we can't quit it. Lead stops X-rays dead, stores electrical energy better than any alternative, and possesses one superpower no other metal can match. How does rock containing lead sulfide become the shields protecting radiologists? Why do we mine fresh ore when mountains of old batteries exist? Stay with us. You'll discover why lead is simultaneously essential and deadly, and the shocking secret making it the most recycled material on Earth. 99% returns to use forever.
Our story begins in Missouri's Lead Belt, America's primary source. Unlike flashy gold mines, lead operations look industrial, almost boring. Massive drills bore 800 feet down, following veins of galena. lead sulfide ore appearing as metallic gray crystals. Each ton of ore contains just 3% lead. The rest is worthless rock requiring removal. Underground, miners work in perpetual darkness, drilling blast holes into rock faces. The lead content makes galena unusually dense. Lift a basketball-sized chunk and it weighs like a bowling ball. You feel lead before you see it, explains one miner. Galena has this heft that surprises you every time. Explosives fracture the ore. Loaders scoop rubble into trucks, climbing back to surface through spiral tunnels taking 20 minutes to traverse.
Topside, the crushing begins. House-sized jaw crushers reduce boulders to gravel, while workers monitor from control rooms behind thick glass. Lead dust is insidious, invisible particles that accumulate in bones, causing damage that appears years later. Modern facilities employ enclosed systems, but older operations tell different stories. Walk through a 1970s lead smelter photograph. Workers in street clothes, no respirators, covered in gray dust. Many develop neurological problems by age 50. The industry learned hard lessons about lead toxicity. Today, air monitoring systems track particle counts continuously. Workers shower before leaving. Clothes stay on site. Blood tests happen monthly. One manager puts it bluntly: respect lead or it destroys you. There's no middle ground.
The ore enters roasting furnaces heated to 1,400 degrees. Here, sulfur burns away as sulfur dioxide, captured and sold to sulfuric acid manufacturers. What remains is lead oxide, a yellow powder looking harmless but deadly if inhaled. The roasting building operates under negative pressure. Air flows inward, never outward, preventing escape of lead-contaminated atmosphere. Watch the roasting process through observation windows. Yellow flames dance over tumbling ore. Operators adjust oxygen flow constantly. Too much air, lead oxidizes excessively. Too little, sulfur remains. Getting it wrong costs millions in lost efficiency. The roasted material, called calcine, moves to smelting via enclosed conveyor belts. Nothing touches open air. The paranoia about containment isn't regulation theater, it's survival. Lead contamination cleanup can bankrupt companies.
Blast furnaces reduce lead oxide to metallic lead through carbon chemistry. Coke, purified coal, burns at 2,000 degrees, creating carbon monoxide that strips oxygen from lead oxide. Liquid lead, melting at just 621 degrees, pools at furnace bottom. Picture the tap. Workers drill through clay plug. Molten lead, silvery and dense, flows into molds, creating 90-pound ingots called pigs. The metal moves like mercury, forming perfect spheres when droplets fall. Lead's density is deceptive. A 5-gallon bucket filled with lead weighs 200 pounds, impossible to lift. Ancient Romans made lead pipes by pouring molten metal into sand molds. The same basic process works today because lead's properties haven't changed in millennia.
Refining removes impurities through clever chemistry. Adding zinc causes copper to rise as dross skimmed off surface. Calcium treatment removes silver. Lead and silver frequently occur together geologically. The final product achieves 99.99% purity. This refined lead feeds manufacturing plants producing batteries, radiation shielding, and specialized applications. But here's where the story shifts. Increasingly, smelters don't process mined ore, they process old batteries. Secondary smelters, as they're called, have grown to dominate the industry. Why mine lead when every dead car battery contains 20 pounds ready for reuse? The economics are brutal. Recycled lead costs 40% less than mined lead. Primary smelters struggle competing. Many shut down, unable to match prices of operations running on discarded batteries. Battery recycling begins at collection centers, where mechanics and scrappers deliver exhausted batteries by the thousands. Workers drain sulfuric acid into neutralization tanks. Each battery contains about 2 gallons of corrosive liquid that can't enter recycling stream. The acid gets neutralized with lime, creating calcium sulfate, sold as drywall ingredient. Nothing wastes. Drained batteries move to breakers, rotating drums with internal hammers that shatter cases, separating lead plates from plastic housings. It's violent. The noise resembles continuous demolition. Lead plates sink in water, plastic floats. Simple physics achieves separation. The plastic gets washed, shredded, and sold to manufacturers making new battery cases. The lead plates, still coated with lead oxide from battery chemistry, head to furnaces for smelting. One facility processes 50,000 batteries daily, enough lead to manufacture 12,000 new batteries.
The smelting of recycled lead mirrors primary smelting, but operates at smaller scale with tighter controls. Furnaces melt battery plates at 1,000 degrees. Impurities rise as slag, skimmed continuously. The molten lead flows into casting machines, producing standardized ingots shipped to battery manufacturers. Here's the remarkable part. A battery recycled today will be back in a new battery within 30 days. The loop is that tight. And that battery will get recycled again in 3 years when it fails, and again and again. Lead never wears out. Its atomic structure remains unchanged, regardless of how many times it melts and resolidifies. The lead in your current car battery might have started life in Roman plumbing, been refined into medieval type, reformed into ammunition, and now cycles through automotive batteries. Lead is functionally immortal. Lead's history intertwines with civilization's darkest chapters. Romans sweetened wine with lead acetate, called sugar of lead, not knowing it caused madness in emperors. Medieval alchemists poisoned themselves studying it. The gasoline industry added tetraethyl lead as anti-knock compound in 1921, despite knowing its neurotoxicity. For 50 years, automobile exhaust sprayed lead over every city, poisoning children and causing measurable drops in IQ. The phase-out began in 1970s as evidence became undeniable. Removing lead from gasoline represents public health's greatest victory. Childhood blood lead levels dropped 90%. Paint bans followed. Today, lead use concentrates in batteries, radiation shielding, and specialized industrial applications. We've learned to respect lead's toxicity while exploiting its unique properties. The metal that once poisoned Rome now powers modern transportation, but safely, contained, recycled endlessly. Carbon emissions dropped 72% producing recycled lead versus mining virgin ore. Industry saves $63 billion annually through battery recycling. Processing scrap uses 65% less energy than conventional smelting. Here's the secret we promised. Lead achieves 99% recycling rates, the highest of any industrial material. That car battery has a 99% chance of being recycled properly because it's worth money. Scrappers pay you for dead batteries. Mechanics collect them religiously. The economic incentive creates a closed loop more efficient than any regulation could mandate. From ancient Rome to modern recycling, the transformation completes. We've learned that some materials are too valuable to discard, too dangerous to mishandle, and too useful to abandon. Lead will never be green, but it might be the perfect example of circular economy functioning through market forces. That heavy metal under your hood has been serving humanity for millennia. It'll still be serving our descendants centuries from now, because lead never truly dies. It just waits to be reborn.
More than half of Earth's entire weight is iron, 32% of the planet's mass. Earth's core is a gigantic ball of molten iron the size of the moon. But iron rules on the surface too. Every second, humanity produces 60 tons of steel.
2 billion tons per year. That's more than all other metals combined. 95% of all metal used by civilization is iron and steel. Without iron, there'd be no skyscrapers, bridges, ships, cars, or trains. How do fiery rivers of molten metal at 3,600 degrees emerge from red ore in city-sized quarries? You'll see explosions in quarries, blast furnaces as tall as 30-story buildings, converters where oxygen turns pig iron into steel in minutes, and rolling mills where 1,000-ton slabs get rolled into paper-thin sheets. Watch to the end. The finale shows why iron holds the world together. This is the story of the metal that built civilization. The Lebedensky Quarry in Russia is one of the planet's largest iron ore quarries. Depth, nearly 2,000 feet. Width, 3 miles. From the edge, you can't see the bottom. A gigantic wound in the earth from which 100,000 tons of iron ore are extracted daily. Excavators as tall as 10-story buildings scoop rock with buckets holding 1,800 cubic feet. One bucket is like a small house. Dump trucks with 360-ton capacity haul ore up the spiral road. Wheels taller than a person. But before loading the ore, it needs to be blasted. Drilling rigs create holes 65 feet deep. Tons of ammonium nitrate explosive are packed into these holes. The explosion? Earth trembles. A wall of rock tall as a skyscraper crashes down. A dust cloud rises 3,000 feet. After the dust settles, excavators begin work. The ore is reddish-brown, sometimes almost black. Magnetite and hematite, iron oxides. Iron content ranges from 30 to 60%. The rest is waste rock. The ore goes to a processing plant. Massive cone crushers grind bus-sized chunks. The noise can be heard for miles. Ore gets crushed to fist size, then to gravel, then smaller. It enters ball mills, steel drums 20 feet in diameter, 33 feet long. Inside are hundreds of tons of steel balls. The drum rotates, balls drop, grinding ore into fine powder. After 8 hours of grinding, you get reddish-brown dust. It's mixed with water, creating pulp, liquid slurry. This slurry passes through magnetic separators. Magnetite sticks to magnetic drums. Waste rock washes away. The concentrate contains 65 to 70% iron. From this, they make pellets, granules the size of walnuts. Wet concentrate gets rolled into balls on special drums, then fired at 2,400 degrees Fahrenheit. Pellets harden, becoming rock solid. These pellets are raw material for blast furnaces. Each plant produces millions of tons of pellets yearly. They're loaded onto trains and shipped to steel mills. A blast furnace is a steel tower 330 feet tall, 46 feet in diameter. 30 stories of pure metal and fire. Lined inside with 3-foot-thick fireproof brick. Internal volume, 176,000 cubic feet. Iron ore pellets, coke, and fluxes like limestone or dolomite are loaded from the top, in layers, like a layered cake. Several hundred tons at a time. From below, through tuyères, openings in the walls, hot air is blown in. Air temperature, 2,200 degrees Fahrenheit. Pressure, 4 atmospheres. Coke ignites. Temperature in the furnace's lower section reaches 3,600 degrees Fahrenheit. Pellets slowly descend, heating up. Different reactions occur at different heights. First, moisture leaves the ore. Then, at 930 degrees, iron oxide reduction begins. Carbon from coke strips away oxygen. At 1800 degrees, ore becomes spongy iron. At 2700 degrees, iron melts. Drops of molten metal flow down. At the furnace bottom, molten pig iron accumulates, an iron alloy with 4% carbon. Pig iron temperature at the furnace bottom is 2,700 degrees Fahrenheit. It glows blindingly white with an orange tint.
Pig iron is denser than slag, so it stays at the bottom. Slag, molten impurities and fluxes, floats on top. Every 4 hours, they open the tap hole, an opening in the furnace's sidewall. Pig iron tapping is a fire show. A stream of molten metal flows down channels. Sparks fly dozens of feet. The brightness requires dark glasses to watch. Pig iron flows into massive ladles on railroad cars. One ladle holds 300 tons. It's a locomotive made of molten metal. The ladle gets covered to prevent cooling and shipped to the steelmaking shop. One blast furnace operates continuously for years. Stopping is catastrophic. Metal would solidify inside. The furnace produces 10,000 tons of pig iron daily. That's like 100 railroad cars. Major steel mills have 10 to 15 blast furnaces. But pig iron isn't steel yet. It's brittle due to high carbon content. Steel is needed, an alloy with less than 2% carbon. Pig iron gets poured into a converter, a massive pear-shaped vessel 33 feet tall, lined with fireproof brick. It holds 350 tons of molten metal. The converter tilts, pig iron pours in, steel scrap is added for cooling. The converter returns to vertical position. An oxygen lance, a tube 20 inches in diameter, lowers from above. Oxygen flow begins. A jet of pure oxygen at 150 pounds per square inch pressure strikes the molten metal. Violent reaction begins. Oxygen oxidizes carbon, silicon, manganese, impurities in pig iron. These exothermic reactions release enormous heat. Temperature rockets to 3,200 degrees Fahrenheit. Metal boils and churns. Flame tongues several feet high shoot from the converter mouth. Sparks and molten drops fly everywhere. The blowing process takes 20 minutes. In this time, 350 tons of pig iron become steel. Carbon burns down to 1% or less. The converter tilts, steel pours into a ladle. The molten metal glows blindingly white at 2,900 degrees Fahrenheit. Alloying elements get added to the ladle. Manganese, chromium, nickel, molybdenum, depending on the steel grade needed. They mix it by blowing argon through. Then steel gets cast. There are two methods. First, continuous casting. Molten metal pours into a crystallizer, a water-cooled copper mold. Below, a solidifying blank emerges, a slab 8 inches thick, 6.5 feet wide. It glows red. Surface temperature around 1,800 degrees Fahrenheit. Gas cutters slice the slab into 33-foot lengths. One slab weighs 25 tons. Second method, casting into ingot molds. Steel forms. This creates ingots up to 50 tons. These ingots and slabs are semi-finished products. They go to rolling mills. There begins the final transformation, turning thick blanks into thin sheets, rails, or beams. Slabs heat in reheating furnaces to 2,200 degrees Fahrenheit, red hot. Then they go to the rolling mill. It's a line of dozens of rolls, steel cylinders 3 feet in diameter weighing dozens of tons. Rolls rotate toward each other. The red-hot slab enters between rolls. They squeeze and roll it. The slab gets thinner and longer. It passes through the next pair of rolls, even thinner, dozens of times. An 8-inch thick slab becomes a sheet 1 to 2 millimeters thick. Length grows from 33 feet to over half a mile. Rolling speed on finishing mills reaches 50 miles per hour. Red-hot steel ribbon flies through the mill, sparks flying everywhere. Temperature drops to 1,400 degrees Fahrenheit, metal darkens. The strip cools with water, winds into giant coils weighing 20 to 30 tons. This is hot-rolled steel, the foundation for car bodies, appliance housings, building structures. Global steel production is 2 billion tons yearly. China produces over 1 billion tons, half the world's output. India, Japan, the US, Russia are other major producers. Steel is infrastructure's backbone.
95% of metal structures are steel, from skyscrapers to tin cans, from tankers to paper clips. Iron and steel are civilization's skeleton. Iron is the oldest metal after copper and bronze. The Iron Age began 3,000 years ago. First, iron came from meteorites, ready-made metal fallen from the sky. Egyptian pharaoh Tutankhamun was buried with a meteorite iron dagger. Smelting iron from ore was learned by Hittites in Asia Minor around 1200 BC. They kept the secret for centuries, but technology spread. Iron weapons were stronger than bronze. Iron plows worked soil better than wooden ones. Civilizations with iron defeated civilizations without iron. Medieval times, iron was made in small furnaces. The Industrial Revolution began with blast furnace invention in the 18th century. Early furnaces used charcoal. Later, they switched to coke from coal. The 19th century brought the converter process, rapid pig iron to steel conversion. Bessemer, Martin, Thomas, names that changed the world. The 20th century was steel century. Skyscrapers, bridges, ships, automobiles. Without steel, there'd be no modern world. And so, traveling from explosions in 2,000-foot-deep quarries through giant crushers and magnetic separators, through 300-foot-tall blast furnaces at 3,600 degrees and converters where oxygen burns out carbon in 20 minutes, through rolling mills where 8-inch slabs become millimeter-thin sheets, steel emerges, the metal that built civilization. 2 billion tons per year. 60 tons every second. The metal everything around us is made from. Every skyscraper, every bridge, every car, every ship. It's iron, mined from red ore, remelted in fire, rolled into sheets. More than half of Earth's weight is iron. The planet's core is molten metal. And on the surface, iron rules. 95% of all metal is iron and steel. From nails to bridges, from paper clips to skyscrapers, iron holds the world together. Without iron, humanity would collapse back to the Stone Age. No machines, no electricity, no internet. Everything's built on iron. From fiery rivers of molten pig iron in blast furnaces to steel beams holding up skyscrapers, iron is the foundation, the base, civilization's skeleton. Metal of the gods that became metal of the masses. The most abundant, most important, most irreplaceable. Iron, the metal that holds the planet together.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this: more than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called tuyeres. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steelmaking requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this, alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised. Every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress, and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter, where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel; coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyères, air heated to a scorching 2,200 degrees. Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 degrees, 1,530 Celsius. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 degrees, 1/200 Celsius. Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the River of Fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds, or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key or barometer of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces.